Yeah, that's what I remember from this area.
Don't be so negative, Martin.
He's always negative. He cannot help himself.
This is.
I need to see. Where's that?
I try to be very positive, but
Try. Fail all the time, miserably.
It's as good as things get, you know.
Good. Okay. Excellent. I think we are ready to roll. Let me share the screen. And once again, I like to. Can you guys see the presentation?
We see the screen, yes.
The presentation, no, the screen?
No, not the presentation.
Oh, I see. Let me stop this. Maybe I thought they did Microsoft PowerPoint. We can try that. The presentation now or the screen?
No, the slides.
The slides, just the slides, you mean?
Mm-hmm.
Okay, good. All right, so thank you once again, everybody, to join us. It is my distinct pleasure today. We have online SPICE and SPIN+X seminars organized by the Spin Phenomenon Disciplinary Center that I run together for the time being for a few more weeks, maybe with Karin Everschor-Sitte, and in collaboration with Latent and Mainz, SPIN+X Collaborative Research Center, led by Martin Schliemann, who just recently got a very beautiful haircut, Purga Hillebrands and Matthias Chloe in Mainz. As you say, this is a webinar format, meaning that you're an attendee but can ask questions on the Q&A. Please answer them or hold up your hand, and you will be given the floor after the talk to ask questions to the speaker. And please go ahead and check out the online seminar list. We continue updating it regularly, and we hope to go through the summer with it as well. Today's speaker is Karin Everschor-Sitte. Of course, started in Cologne. I went to the US for a while and then came back to Germany, Mainz, where we've been collaborating ever since she arrived 6 years ago. And they started her own group as a Minuta group here very successfully. So successful that unfortunately somebody else took her away. And she has started since April 1st, her professorship, W3 professorship in the University of Duisburg-Hessen, where she's now in the middle of transferring the group there. Has several very nice awards, like the Sponsor Prize Award, some DPG, several awards. But having said that, she's extremely active, now going in new directions. And with that, I think that's all I needed to highlight. I think everybody else knows you. So go ahead, Karin, and please share your screen and start your presentation.
Thank you very much, Jairo, for the kind introduction. And I will share my screen now. Is it working?
Yeah, it's working.
So it's my pleasure to give a talk about magnetic skyrmions for unconventional computing and revealing latent information. To give you an overview, what I would like to talk about, first give you a short introduction into magnetic skyrmions, and then tell you how skyrmions could be good for unconventional computing. And in particular, two parts. A very short part, which I mentioned, is how skyrmions can be interesting to build a reshuffler device for stochastic computing, and an extended part where I would like to talk about skyrmions for reservoir computing. So this work has been done mostly in collaboration or initiated with George Boryanov. And now Jake Love from my team, who's a PhD student, is leading these efforts, and we're collaborating with the MUMAX team, in particular, Jonathan Lydiard and Jerome Mokas. In the last part, I would like to talk about data analysis, a new tool for my spectroscopy, and here I would highlight the collaboration with Ilya Horenko, who's a data scientist and a mathematician by training. So let me start by what is a skyrmion, and you can look it up in Wikipedia, and then you'll find the wonderful sentence that a skyrmion is a homotopically non-trivial classical solution of a nonlinear sigma model with a non-trivial target manifold topology. So even if that's the definition, then what you can get out from it is that you are dealing with an object that you can define precisely mathematical. And as such, it can occur in different regions of physics. And it has been originally introduced in 1959 by Tony Skyrm, from where it also got its name, in particle physics. And here we're talking about magnetic skyrmions. And to better understand this magnetic structure, it's colored in a color code. So red meaning that the spins point upwards, blue meaning they are pointing downwards, and yellow means that the local magnetization direction is somewhere in the plane. So how can you get such a structure? You can start from a hedgehog and then open this hedgehog and project it down the plane. Or you can see it more from an animation done by Jan Marcel, previously Jan Müller, where you really take your hedgehog, open it, and then project it down to the plane. Or if you do it the other way around, you start from your skyrmion and then map it back to a sphere, and thereby you see that you're dealing with a certain topological object. So we can have these skyrmions where we just open them and project them down. They are called nail-like, but we could first also take a comb this hedgehog a little bit, and then they get an additional in-plane twist here, which are called block-like. But in principle, you can have even all structures in between, and you can have even more fancy spin structures shown here, which most of them have also been experimentally seen by now. So a bit about the history of magnetic skyrmions. So they have been theoretically predicted by Bogyanov and Jablonski in 1989. And they have first been experimentally observed in 2009 in the form of a skyrmion lattice. So here you see the corresponding Newton scattering pattern for the skyrmion lattice. So for skyrmions to have, you need to break inversion symmetry, because if you go here from the left spin to the right spin and you cross the middle, then you need to turn either left or you need to turn the twin spins to the right. So you can break inversion symmetry either spontaneously or by the lattice itself. And if you also look at it, then what you need to have a skyrmion is at least two types of competing interactions. So one interaction scale that would like to have all spins pointing upwards. So when you go around the circumferences, the main structures are ferromagnetic. And another one that would like to have this twist, which you see when you cross the magnetic structure. And this explains why you can have skyrmions in so many materials, because the fundamental ingredients that you need to have them occur in very different materials, like metals, semiconductors, insulators. You can have them in bulk structures where you break inversion symmetry, for instance, by the crystal, or in thin films where you also break it by the interface. You can have them at low temperatures and also even above room temperature, which was another breakthrough in this field of skyrmionics. Also, what you can easily understand is if you play around with these two interaction scales that you want to mix in, if you take more from the one or the other, then you can engineer the size of these skyrmions. By now, you can detect them by various experimental techniques. And you can even create, manipulate, and destroy them by various means. So you can really think of like particles that you can write, delete, and also move around. So why are skyrmions interesting? One thing is because of what I've shown at the beginning. So this mapping to the sphere shows that they have a special topology. And this has been shown to give them an additional stability. Another thing is that they can be rather small and that they occur above room temperature, which I just mentioned. And one thing that we found already quite early on during the time I had the chance to write my PhD thesis in the group of Achim Roche, together with the experimentalists group of Christian Fleiderer, was that we found that if you have a lattice of these skyrmions, they couple very nicely to electric currents. So they couple to an order of 10 to the 6 ampere per square meter, which is 5 orders magnitude lower than you would typically need to move a domain wall. And besides that, they have very interesting physics. Because of the Magnus force, they show a so-called skyrmion Hall effect. So once you have an electron flow in this material, the skyrmions just don't move only along the electron direction, but also at an angle to it, giving to it a skyrmion Hall effect. So taken all together and their appearance in device-relevant systems, of course, the question arises, what are potential applications for skyrmions? And for this, if we say we have skyrmions, what can be skyrmion-based devices? Probably the most studied potential application is the skyrmion racetrack memory. So the racetrack memory is a device concept suggested by Stuart Parking, where you have lots of domain walls on a one-dimensional nanowire, and the information is encoded in the different domains. And there was the suggestion by Albert Fair to, instead of using domain walls, to put skyrmions on the track. So it does have some advantages because you can see these skyrmions don't touch the edges of the wire. So in principle, when you have an edge roughness, then these domain walls could get stuck, but these skyrmions can move around them. But it's also known that it has certain disadvantages because of, for instance, the skyrmion Hall effect, which I've just mentioned, which can occur that the skyrmions will move at an angle and then could be erased at the sample edge. There are several works how to get rid of the skyrmion Hall effect, and here I just summarize a few. But basically, so far you can categorize them in two categories, and in one you use the concept of 1 ± -1 being 0. So what do I mean by that? It's probably most easily understandable in synthetic antiferromagnets, where you have one skyrmion that's orientated in a way that you have a red core in the middle, and one where you have a blue core. And then the idea is that the ones with the red core would feel a force towards the left and along the current direction, and the one with the blue in the middle towards the right and along the direction. But if they are strongly coupled, then the forces in the perpendicular direction just cancel each other, and the skyrmion in the synthetic antiferromagnet just moves forward. Similarly, in the case of a real antiferromagnet. The other part to get rid of the skyrmion Hall effect would be to use an additional symmetry breaking. So you see all these skyrmions are a little bit more complex in combination with spin-orbit torques to get rid of such an effect. Okay, so we have seen that putting skyrmions on a track can have advantages and disadvantages, but what has been actually done is taking an existing device concept, and instead of putting the domain wall or whatever has been previously been there, just putting a skyrmion there now. But we can also ask the question, what is a device that optimally uses the properties of a skyrmion? And for this, let's just have a look at the domain wall itself. We know that it's basically a one-dimensional object. So any information along the third or the other two directions is not needed. So for the device storage, we only need where is this white line here. For the skyrmion, however, we have in principle more degrees of freedom. So we can move it around in 2 dimensions, and therefore we can either use that it can extend, it can breathe, or that we can move it along 2 directions. And this gives some additional features. So constraining the motion of a skyrmion on a one-dimensional track is probably not the most ideal application of a skyrmion. So there has been the suggestion to just pimp up the concept of racetracks towards 2-lane racetrack memories, for instance, by Jan Müller here. But this is still finally one-dimensional transport of skyrmions. So we've been working along 2 directions. One is stochastic computing, one is reservoir computing. And stochastic computing, as I said in the beginning, I'm just going to mention really briefly. So there has been the idea put forward to build a skyrmion reshuffler device, where you basically, as shown here in this cartoon picture from Andreas Donges, where you basically take in skyrmions, put them into a mixer, and they leave at different times. So this has been suggested by Daniele Pina in the group of Julie Collier while he was there. And it has been recently built by Jakub Zadzworska when he was in the group of Matthias Kloy. And here you see the 2 chambers where you can put skyrmions in, they get mixed around, and they exit at different times based on thermal motion. And the idea is to take an incoming signal, which is shown here in blue, and to reshuffle the signal for stochastic computing into the orange one. But let me now come to reservoir computing. So reservoir computing is a field that has emerged from the field of artificial neural networks. And in artificial neural networks, you typically have nodes, input nodes, you have output nodes, and you have internal nodes, which can be recursively connected. And what has been shown that under certain type of training conditions, it was observed that actually not only the connections here internal were rather fixed, but only some parts here at the end happened. And starting from this observation, a new field arose, which was called reservoir computing. So in reservoir computing, the idea is now to keep all these internal nodes fixed and only train these orange lines here. And one very important part is that reservoir computing does not aim to solve a complex problem directly, but to take a complex problem and map it to something that is linearly solvable. So start from something that is complex and map it to something that is linearly or easily solvable. So what is now the functionality of the reservoir if it stays fixed? So the reservoir projects different spatial temporal events into a sparsely populated high-dimensional space where they become easier to recognize and categorize. So what does this mean? You start from input data in a low-dimensional space, and in my plotting, low dimension means now 2. And then you feed this information through the reservoir, as I'm going to show in an overview slides in a few minutes. And then your reservoir projects the data into a higher dimensional space. And once I'm in a higher dimensional space, I can now draw hyperplanes to separate the data. And now I can easily separate this data. So what is reservoir computing useful for? So it's useful for the recognition and classification of spatial temporal events, like speech recognition, sensor fusion type of applications, where you, for instance, have lots of signals from your car, where lots of sensors are beeping, and you want to combine the signal to interpret it to, for example, a car is coming from the left. And why? What are the advantages of reservoir computing? One thing that is really nice is that you can train for multiple features simultaneously. So to give an example, if you want to do speech recognition, then you can have lots of people speaking, for instance, saying the number 0 or 1. You can train on the number being said, on a male or female having said something, on a child or an adult, and so on. And another advantage is that you don't need to know any details about the reservoirs. But if you don't have to know anything about the reservoir, then you could basically put a black box here. But what of this black box has now to survive? So what actually has to survive is that this picture shown here on the left is still working. And this we can reformulate into certain statements. So what we needed is that this one was a low dimensional space and that one was a high dimensional space. So the dimensionality of the reservoir state must be much higher than the input area. What we also needed is that the data separates. So we need some certain type of nonlinear response. Otherwise the data does not separate. And in case we want to know anything about the history, so if we want to have really these time correlations, then we also need to have a short-term memory in the system. So given these requirements, if we sum them up as a physicist, we can just say that what was required is a nonlinear complex system with a short-term memory. And this we have all over in physics. So this opens up, therefore, then the idea to do pattern recognition with matter. And seriously, you can really do it with any kind of system that fulfills the statement nonlinear complex with short-term memory. And people have done it with water buckets. So they used water buckets and put little pellets on top to characterize then signals and to do reservoir computing with it. Of course, that's not the part that you want to go for, to put everywhere water buckets in your room to do computations. People also studied optical systems and also spintronic systems like the spin-torque nano oscillators from the group of Julie Collier. Before I come to what we have mostly in mind, I first would like to sum up a little bit the idea of reservoir computing with matter. So what do we actually need? So we start with some data that we want to classify, categorize, and so on. So let's say we have input data where people say the number 1 or 2. And now we finally want to put this through our system. So the first step is to bring it into a language that our system understands. So you need to bring this or convert the signals into something that your system understands, which in my case might be voltage signals. And once you have them, you can feed them through your system, which can be any system that fulfills this complex nonlinear with short-term memory. And in my case, it's going to be a spintronic system based on Skyrmions. And then what is your task is to define what you can measure. So you need to build your space that you can measure. And I'm going to show 2 examples, and they will span your high dimensional space. And starting from this high dimensional space, you can now train a linear classifier, so an easy task to do linear regression of the data. So what is the system that we had in mind? George and I started this a couple of years ago. And our idea was to use magnetic or Skyrmion fabrics as a reservoir, and then to put voltage contacts on top and feed voltage signals through this reservoir and through this network. And the idea that we had in mind is basically this. So think about a river filled with rocks and stones, and now you have a water current going through the river. And one thing that is clear is that the water will find the path with the lowest resistance. And another thing that is hopefully clear is that if the current flow gets really strong at one point, it will kind of excite these rocks or like lift them a little bit, and then the current pattern will adjust. So we started off very slowly by just taking 2 voltage contacts, and we had a pinning center here in the middle. And what we need is any type of magnetization dependent magnetoresistive effect. So as I said, for reservoir computing, no detailed knowledge about the reservoir is required. So any type of magnetoresistive effect will do the job in this case. And our computation are going to be on the anisotropic magnetoresistance. Just to let you know that you can even measure Skyrmions by magnetoresistance. So that's a study from 2015 where people have seen in magnetoresistance measurements the difference between 1 or 2 Skyrmions and so on being present. So for a single Skyrmion, what do you see? So we have 2 contacts. We have here a Neil Skyrmion and here a Bloch Skyrmion. And when you compute the current path through them, it looks basically like that. And to get a better feeling, we subtracted what you would get, because for 2 contacts, you always get something round or shaped. We subtracted what you would get for a ferromagnet. And then you can see is that through a Bloch Skyrmion, the current prefers to go. So here it likes to go through, while for a Neil Skyrmion, it rather avoids it. Another thing that you can see once we start pinning these Skyrmions, then when we apply a current or a voltage between these 2 contacts, then these Skyrmions will deform, and therefore you get a different resistance out of it. So you can try to look at it as a device, and then you can measure the resistance that you get as a function of the voltage, and we see that we have a nonlinear IV characteristics. So of course, 1 Skyrmion, the signals are small, and that's actually not the way we want to go, because we also want to have complex, and 1 Skyrmion is simpler. So what we wanted to do is some sort of complex structure, and in the upper plots, you see some Neil type magnetic structures, or Bloch type here, and below you see the current flow, and you see wonderfully that the current has something to do with the magnetic texture. So this is now the reservoir that we used for the results that are shown in the following. And here you see the magnetization again, now in a different color coding, and here the current flow. And one thing from these 3 requirements, so as I said, we need nonlinear, complex with short-term memory. I think complex, you probably all agree, complex we have already. Another thing that is crucial to have is that, of course, whatever you do to your system, when you turn off the drive, it must go back to the same state you started with. Otherwise, it won't be able to reproduce the results. Then you start from some other state. So we must ensure that these skyrmions don't displace significantly for the reservoir to work properly. So how you do this, actually in the experiment, you always try to get them moving. So most of them, they are stuck. So experimentally, there's less of a problem. So theoretically, what we did is we modeled them through grains. But how the details of it don't matter for the concept to work. And then we check that once we apply voltages, then you can see here that these skyrmions start to wiggle around. So they will finally change the resistance and so on. But when we turn off the drive, it relaxes back basically to the same structure that we started with. Okay, so what we now want to do is we want to have finally, which is what we are not yet there, finally we want to have lots of signals that we want to classify. So we started with the simples that we can do. And one of the simple things one can do is one can have a sinusoidal signal or a voltage signal shown here in blue, a square wave signal as a voltage signal that we feed into our structure. And then we observe the resistance shown in red of the device. So this is shown as a function of time. And one thing you can see from this plot is now the short-term memory. So now we already have the second criterion. So how do you see that? For example, look here at 3 nanoseconds. I turn off the drive, and then the signal still persisting in the system. So there is some short-term memory before the resistance is going back to where it started from. Okay, we are still missing the nonlinear part, and this is arising once we keep exciting the signal. So another thing that was pretty bad, which I forgot to mention, just that the resistance signal here was small. So once we start putting a train of pulses through it, then we see that the resistance signal rises by a factor of 10. And this is because after some swinging part, we get a very strong nonlinear response. So the yellow curve would be the linear reconstruction of such signals, so just adding up these signals, and then we would be more or less here. But we see here that we get a very strong nonlinear response. So by that, I've shown you that we have all the requirements needed. So let's now see if we can do pattern recognition. And first, I would like to invite you to just do it by eye. So if you just look at these signals above by eye, you might see that you have, for instance, this one appearing here twice. And this signal here always appears when you first had a sine curve and then a square curve. So for two sequential pulses, you can have a sine, sine, square, 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 sine, sine, square. You see 4 different signals arising. And this you can already see by eye, so you know that it will work. So let's do this a little bit more elaborate. And I would like to show 2 types of defining how the readout is. So how you define your high dimensional space. And the first one is time tracing, meaning that you just take your measured signal and trace it over certain time steps. And then from the signal here, you want to learn about the present pulse, the pulse before, and the pulse even before. And these measured dots here, which are just finally numbers, so like 490 here, will go as an input vector to train a linear classifier for these past, latent, and present pulses. And now you can just take your computer and train it. And what you see is that you can get recognition rates as a function of these resistance traces after like 10 or so. It's rather equilibrated. And then we see we can do a very good recognition of all these pulses. Another possibility to define the high dimensional readout is to exploit the complex magnetic structure in real space. So by this, you could take a one-time single picture of this magnetic structure. So for instance, if you would put like little measurement palettes on top where you could measure the magnetization of the resistance, and then you can use this as an input for your vector to classify the, to train the linear classifier. And as a function of these readout elements, you can get the recognition rate, and you can see that the recognition rate is always very high besides this purple curve. So why is this purple curve special? Well, you always have the choice when to take this snapshot. And if you do the snapshot before the pulse started, of course, your recognition rate is on the level of 50% because you don't know anything about the pulse yet. If we then look back into the past of a time slot now, then we can still get very high recognition rates. So what I've shown you so far is that we have a nonlinear complex system with a short-term memory, and I've shown you that we can do simple pattern recognition by a single measurement even. The advantages to have maybe a Skyrmion reservoir is that it can be rather small and the energy consumption is not too high. And something that is very special for the real space topology is that you have many degrees of freedom. The complexity doesn't have to come with time. And as an outlook, we are, of course, working towards having more contacts on top. As I said, we work for this with the Mumax team, who have already written a code that enables to have more contacts. So let me now come to the second part, or the last part of the talk, data analysis, new tools for microscopy. So for this, I also would like to give a short introduction. Moore's law is, of course, always very much debated, and there is the idea that Moore's law will soon come to an end. But if you look at it economically, Moore's law has already come to an end because you cannot fabricate them smaller and cheaper. So by now, if you make them smaller, they become even more expensive. So we need new approaches. And in this talk, I motivated to use Skyrmions for unconventional computing, or more generally to compute with matter, or to improve hardware for computing, which eventually might be spintronics based. Some of these concepts require going back from digital to analog type of information storing, which is also something that future will show whether this will happen or not, because all our transistor technology is not really made for that. But when you look at it, some of these parts look really bad. We need something new, but no one knows what this new is going to be. But when you look at computer science, still tremendous progress has been made in the recent years. And one key topic is, of course, machine learning. Some of these basics ideas are more than 50 years old. And one key ingredient for the enormous progress is relying on the computer hardware that is available nowadays, in particular graphic cards. Nevertheless, the field is also facing some problems. And one thing that is not too much known is that very often underlying machine learning algorithms are assumptions. So one of them is IID, so identically independent distributed, and Gaussianity. So for instance, this is a picture shown from the measurement of the Skyrmion diffusion, and you can immediately see that not all places are equally populated of these Skyrmions alike, but there are some that are populated with a higher probability and some that are with less probability. So if you look at it from a physical point of view, it's for sure the space is for sure not IID. So it's not identically independent distributed where the Skyrmions would like to stay. Another part is that very often you need large data to train your machine learning algorithm. And whenever you go to large dimensions, you have the curse of dimensions and overfitting problems. Another key problem for us physicists is that very often you cannot measure the things that you're interested in directly, but you need to find ways to go around it, or you need to probe the system such that you get finally to your wanted response, meaning that there are latent effects. So not all the information are directly accessible, but there are latent effects. And one key example of latent effects is this picture. So this shows, or is supposed to show, the first image of a black hole. And as we all know, we of course don't see the black hole directly, but what we see is the features or the signatures the black hole makes on the surrounding, so which is then shown by different signals in the data. This is a very expensive picture, and to get it done, to just summarize it very simply, what you needed were progress in telescopes as well as data analysis. So the data analysis that has been used were Gaussian mixture models, and if you want more details also on the telescopes and on the Gaussian mixture model parts, I listed them here. But what I would like to say is that Gaussian mixture models are not very cheap. So when you increase your data set, then they have a polynomial scaling with every iteration of the computational cost. But still, they belong to the most popular latent inference methods. And what do I mean by that? If you just type it into Google Scholar, you immediately see that you get 1.8 million results for Gaussian mixture models. And just to have a comparison, if you type magnetic skyrmion, then you find about 17,000. So, but what we have worked on is to develop two tools that are cheap meaning where the computational iteration cost is independent of the data dimension, to extract latent patterns. And these are denoted as latent entropy, which tells us something about the stochasticity about the system, and latent dimension, which tells us something about the memory of a system. Okay, and before I tell you more about these tools, I would just to show you where we applied them to one example. So what you see here is actually not a magnetic system, but a microscopy of a mouse brain, so raw video frame. And what you're supposed to see is the flow of transparent fluid through the capillaries of the lymphatic system. So just to give you an idea, if you take the brain of a mouse, then it has actually been recently discovered an anatomic organ that is responsible for the waste clearance, so which can be, for instance, very important for diseases like Alzheimer's. So how is waste being cleared in our brain? So still, when you just look at this raw video frame or you just look at the movie, then you don't see much of these capillaries. When you just take these data and put them through a denoising autoencoder, then you might see some signatures arising where you, for instance, can see here tiny features that arise which show you these capillaries. And the problem why you cannot see is of course, this word transparent. So there is something in the data which is latent because of this transparency. So people have also used the GMM entropy. And when you do that, then you really start to see these capillaries of in the mouse brain. So we have analyzed these data set also with our methods, and then we see far more capillaries, not only on the surface where the image was cut, but also deeper lying bulk lymph capillaries. So to go towards magnetic systems, we have studied actually the Ising model, the micromagnetic model, and magnetic imaging data. And the idea was to first go something which we can really control, the 2D Ising model, which you can in principle solve fully analytically, towards something a little bit less controlled, towards experimental magnetic imaging data. Before I show you the magnetic results, let me give you a little bit of a background. So what is behind those tools? So finally, it is very mathematical. So we're dealing with two data sets, X and Y. And whenever you have two data sets, then there can be no relation between these data sets, which is a Bernoulli process, which is, for example, when you throw a dice and you flip a coin. So they have nothing to do with each other, hopefully, if you didn't cheat. Whereas on the contrary, in the animal world, where the rabbit population is very much related to the fox population the next year and so on, you have lots of Markovian processes where the data sets do depend very much on each other. And for these, typically, you need a full matrix to describe how you can get from the different states of X to the different states of Y. But as we have seen, there could be something in the middle where we have latent processes. So it's not fully dependent, but you have some hidden process in the middle, some latent process in the middle. And then it splits up that you can have from the mapping from X to the latent variable AK and then to Y. And the nice thing about it is then you don't need a full relation matrix, but you can split it up in two matrices, which can be then two smaller matrices, where you already see that it's cheaper in storage. But I'm also going to show, or at least note, that it's also cheaper in computation. So another way to visualize these things is to say that you have all the possible input states from X, you map them to all the possible latent processes, to all the possible Y states. And here you can see also the idea of having memory in the system and predictability. So that's easiest to see when you look at the Bernoulli process. So in this representation, it would mean that all the states, whatever you had, like think about your dice, you had a 1, it would be mapped to L1. You had a 6, it would be mapped to L1. So all the memory is gone. But the predictability then on your coin flip is still how the errors here are distributed. And for the Markovian process, it's just that this latent variable still has n entries. On the algorithm itself, I'm not gonna go too much into detail, but just to make clear, it's a complete algorithm. So given data, you can just follow this algorithm and compute the average latent entropy and the average latent dimension. But one thing that we make use of is that we don't say we have a fixed case. So it's a little bit like a path integral approach, where we say we allow for all dimensions, to allow for all k here, and then weight them with this certain probability, in that case, the posterior probability to occur. Oh. And thereby we get the average latent entropy. So for the Ising model, what we did is we took a square with which had a small box that had a different exchange parameter, where it is deviated by 1%. And then what you know is if you compute the mean value and you're below the critical temperature, then you might find this box in the mean. But if you go above the critical temperature, then at some point the spins are not ordered, and then you would not be able to recognize where this box is just from the spin dynamics. So you can use also lots of other tools, but to come towards an end, what I would like to emphasize is that the expectant latent entropy can still resolve this box also above the critical temperature. And this you can also analyze more quantitatively. So if you look at the pattern recognition quality, you see that for the latent entropy tool, it's very high, even above the critical temperature, and also depending on the relative strength of the heterogeneity. Another key thing to mention is that the computational time does not increase with the statistic size, which is different for the GMM entropy. So here's the other model that I would like to show, which is a micromagnetic model. So we basically modeled LLG dynamics with some thermal parts. And here's the spin dynamics that we observed, or some movies that we looked at. And what we actually did was looking at some part where we have a box that has a different anisotropy. And based on that, we also did the same analysis. So we computed the mean. And for instance, in the mean, you could see something in the MZ component, but not the DMX component. But in the latent entropy, we saw it in both. And what we did then additionally is to add noise onto the data, which, for instance, would happen when you measure, where you have additional measurement noise due to whatever reason. And an interesting thing is that even with adding noise on the same size of the signal, our tool is still able to recognize these boxes. So now we looked at experimental parts. So these are data from the group of Matthias Klois, or the ones that are also used for the Skyrmion thermal motion. And here you can see these Skyrmions wobbling around. And you see already by eye that there are some sort of material defects, for example, where there's this warmth effect that might not be fully moving and so on. And some of them stay at places where they like to rather stay. And when we analyze it, we also resolve a lot of material defects from the data. So, and another thing that we observe is that if you look very closely, you have some more blue part here, some more yellow part here. So this could, for instance, indicate towards a temperature gradient that could be present in the data. And one very interesting thing is that given the data, we can even see some small squares here. So I just highlighted it here. One has to really zoom into the data, and thereby we can show how much the group that has produced this data used video compression. And we also looked at different data. So this is a data set from the group of Axel Hoffmann, which is an earlier data set. So here the idea was not to have this thermal motion, but to blow skyrmions, to produce them from domain walls and then blow them out. And here we see even more material defects arising. So to sum up this part, what we have developed were two tools that don't cost so much. In terms of computational cost for the extraction of latent pattern, the latent entropy, and the latent dimension, which tell us about memory of the system and about predictability. And as an outlook, Sarah Jenkins, who's a postdoc in my team, is now looking towards a strategic categorization of the magnetization data based on these tools. And with that, I'm at the end of my talk. I would like to thank my collaborators, also my team for all the great support, and also my family for all the support. Thank you very much.
Okay, excellent. Thank you very much, Karin. So now we'll have questions. Please raise your hands if you would like to ask questions. I think the first one is from Jack. Let me promote you here. So Jack, go ahead and ask your question if you can. Unmute yourself. You can you, I don't know.
Hi there. Can you hear me okay? I'm in a slightly noisy room.
Yeah, no problem. Yeah.
Okay, amazing. Yeah, thanks so much for a great talk. Really nice stuff, really nice system, and yeah, really beautifully delivered. So thank you very much for that. I'm just going to get my question up so I can read it properly. So I'm actually working on a not too dissimilar system that we've come up with. It's not Skyrmions, but there's nanomagnetic reservoir prediction. So we've got a system that ticks the boxes that you have described. So we have this large space, this very nonlinear response, and memory. So we've been benchmarking the reservoir behavior, and one of the tests we've used is the Mackey-Glass equation. Have you tried to do any predictions of that using your system?
So wait, let me just go back to the slides, but for this I probably have to share and unshare again, sorry. So the idea is that right now we are characterizing the reservoir computing more closely. So far what we had were very little data sets. So, and it was restricted by the code that we were using. So we only had 2 contacts, and this allowed only for this type of data set. So I can just share my screen like this. Do you see it now? So, and this was kind of really maybe a little bit of a longer train, but this were the only data set, but it was limited by computational cost. So now we are training more data sets, and then a characterization is better. So Jake from my team, we have established now methods on different parts. So actually on each of them, so complex, stability, short-term memory, nonlinear. And we will apply them. So some of them will be task or are task agnostic, and we have tested them already. And there will be also parts that are non-task agnostic, and we are trying to do this now.
Thank you very much. So that's really informative. Thank you. One of the specific question I had is that we got very good prediction results with our reservoir. We're quite happy with ourselves as people that don't really understand how these things work. And then we thought that we would just test as a sanity check to run the prediction without our reservoir, just running simple linear regression on the raw data. And we were quite shocked to find that this does an excellent job of predicting it. So I just wondered if on any of the tests that you've presented today, have you benchmarked it using simple linear or ridge regression with no reservoir?
So as I said, so far I have not shown any of the benchmarking tasks. So these we have partially, but I didn't show them yet. But I can tell you that from the group of Julie Collier, they had a similar issue. So they first had done the prediction with and without the spin-torque nano oscillators, and they had a similar issue showing that they have also good training parts. So, and one key part is, what do you do before you feed something into your signal? So whatever you do in the pre-processing, of course, affects of what you are actually doing to the system. So therefore, if the pre-processing takes you a lot of effort, then why should you do reservoir computing at all? Then you can do it directly. So there's always, and I think, yes, you're right, one needs to test this. And one needs to test this also strategically. So how much is the system at hand actually helping?
Excellent. Let's have the next one for Burkhard, Giovanni.
Hi, Karin. Thank you very much for the great talk. So I have a very simple question. Is about your slide 53. So 53, I was wondering, which is the type of noise you are adding to your data?
So I didn't show both. So we added one-time Gaussian noise and one-time non-Gaussian noise.
So it's white noise. So it's a Gaussian distribution, zero mean, unit variance.
Yes, we tested Gaussian noise and we tested non-Gaussian noise. So the reason why we tested Gaussian noise first was that some of these measures we took as a comparison typically are good for Gaussian recognitions. But then we added even non-Gaussian noise, so these are not shown.
Okay, but which are the results when
It's similar. So we have also started to get mathematically more deeper into why our measurements are noise insensitive, and partly one can prove this mathematically. So all those results that I've shown about the algorithms are proved fully mathematically by Ilya Urenko.
Okay, last question is same topic. So which is the amplitude of your noise? So did you have a systematic study as a function of the amplitude, or is it just?
So probably the answer is no. What we did, we edited it so much that it was clear that it doesn't help for these data. So there is, of course, a theorem that the longer you measure, the more you get rid of your noise. Okay, so there is a theorem that if you have a large noise signal, then you just need to measure longer. So here we made it the other way around. We had a given data set and we keep adding noise. And at some point there is, based on some mathematical criteria, that you can no longer recognize it with these type of measures.
All right, thank you very much.
Okay. So Burkhard, go ahead and you can unmute yourself and ask a question.
Beautiful talk, Karin. I have a question. Can you show up again view graph number 37? Because that really triggered me.
37, sorry. Here?
37, this one, yes. I was wondering about the internal dynamics you have in the system and how that actually modifies the temporary memory or the short-term memory you were mentioning. If I look with my eyes of a spin dynamics guy onto this view graph, it is very clear what you see under C1, C2, C3, C4, and so on, because you have different waveforms, they have different Fourier components, they excite different dynamics, just precession, nothing else, of very small elements actually. It's probably just single particle precession, so it could be actually very well understood.
No, it's this system. So it's this system. So it does this.
Yeah, but I mean, you have precessions there.
Mm-hmm.
You must have precessions there, and of course that determines the answer of the system very much. So how much is the internal dynamics considered in all your work? I know it's always implicitly considered because you do numerical simulation, hopefully with small enough element sizes. But is there a more analytic or somewhat better to understand approach to?
So the key idea is that none of this matters at all. So the key idea is take whatever you want. And look, so first of all, it's not very simple because you have all these grains and you have all these parts. So it's finally a very complex system. And of course, if I change like here my grains a lot, then I get another magnetic structure out.
Yeah, but Karin, that is not right. If you go back to 37.
Yeah, but that's what we modeled. So this is the setup that we used for 37.
Yeah, and if you take 37, not 36, please.
Sorry.
Yeah, because you show there the forms. If you have a form like C4 sine wave, of course you only excite any dynamics with low frequencies, which you see. And if you excite, for instance, C3, which is just a rectangular form, it's very, very clear that you also excite higher, let me call it simply higher dynamics. I think you understand what I mean. And so there's this distinct difference, which is just given by the intrinsic properties of the system and the question you ask to the system before you measure the dynamics.
So yes, what we are. So I can just show you more plots. So so if you start applying frequencies that are higher, okay, that are too high. So yes, we are close to the resonance system of the resonance frequency of the system. So if we go very far away from it, like for instance, we go much higher, then of course at some point we lose the idea of the nonlinearity, because if you just poke your system very frequently, it just feels a constant pressure, so it's not able to do this resonance motion. Okay. If you go very slow, then at some point you're out of the memory. So what happens then is that, for example, the system just relaxes already again before the next pulse comes. Yes, so these things we have. And the key idea is here that what you need is this nonlinear short-term memory complex, that's it. And then you can use it for reservoir computing. How good it is then depends on the precise system properties.
So is there dynamic storage? Is there storage of information simply because of the dynamics? Because the system is still...
Yes. Okay. So the dynamics is in the system, and then you can basically read it off here. Can you see my mouse? Yeah. You can basically read it off here. Okay, that's the time scale where the system has memory. Okay, and this is intrinsic to the system itself. Of course, there are ideas to use systems that have multiple intrinsic timescales. So that's something that is a key property if you want to do it on different timescales, and then you can even train on different timescales simultaneously. But the short-term memory is given by the natural system's frequency.
Okay, thank you.
Yeah. So excellent. Do we have any more questions from the audience that would like to put to Karin? So doesn't seem to be the case. So with that, I think once again, in this case, I think we're 170 participants for attending, and Karin for a wonderful, very clear talk. Oh, okay. I think people are just applauding by raising their hands if you enjoy the talk. And then next week, please please join us once again. I think I have to look who's the next one next week. Do you know who's the next one next week? I think it's it's James. James, analyst from Berkeley, will join us, and some very exciting new concepts in
Jule, komm jetzt losspielen, auf geht's.
Okay,
Frag mal, auf welcher Mannschaft du mitspielen kannst.
Sorry. I think
Danke.
Yeah, I think, okay, hang on. So with that, let me stop the recording and the live streaming. It's ended. Yeah.